Hello, I am Kumar Rahul and I am here going to represent one of the topic from electromagnetic named electromagnetic induction. Let's talk about electromagnetic induction. Electromagnetic induction. Electromagnetic induction. EMI. Short form is called EMI. So what is this electromagnetic induction? The word itself explaining the concept that electromagnetic induction means induction of electricity due to magnetic phenomena. Induction of electricity due to magnetic phenomena is known as electromagnetic induction. In present age, we know that there is a relation between electricity and magnetism, but it was a very different picture in the early decades of the 19th century. People believed that the electricity and magnetism are two separate parts. But after the experiment of Oersted, Ampere, and many others, they could able to prove that the current carrying conductor or any coil can produce magnetic field in its surrounding. Hence, it is proved that the electricity and magnetism are interrelated. Obviously, a natural questions arise on that time whether it is converse is also possible. It means if electricity could able to produce magnetic field, is it true that magnetic field could also produce electricity? By keeping in mind this idea, Faraday and Henry start numerous experiences. They started numerous experiments, and what they have observed, they have observed the following. What they had did, they did, it taken a coil. They have taken a coil and connected it with a galvanometer and bring a magnet. What happened? When this magnet was static, when this magnet was held stationary, there were no deflection observed in the galvanometer. No deflection observed. When this magnet was kept static near this coil, no deflection were observed. But when this magnet was kept moving towards the coil, what happened? Could you assume anything? What will happen if we brought this magnet towards the coil? There occurs a magical things. There occurs a deflection in the galvanometer. When they brought closer to the coil, this magnet will be when brought closer to this coil, they start deflection in particular direction. They have carried out many experiments. So what happened? What happened? Now, when they start moving away it from the coil, this time again deflection were observed. Deflection was shown by the galvanometer, but the direction was opposite to the previous one. When the magnet was kept stationary, no deflection were observed through the galvanometer. When this magnet were keeping closer, bringing closer to the coil, it starts showing deflection in particular direction. When it was kept away from the coil, it starts showing deflection in the some other direction, opposite to the previous one. Now, they did what? They just changed the polarity of the magnet. Now, instead of bringing north pole towards the coil, they start bringing south pole towards the coil. When it was static, no deflection were observed. When it was brought closer to the coil, it starts showing deflection but opposite to that of north pole. And when they are keeping away from the coil, it starts showing deflection opposite to the previous one. Not only the magnet, but a current carrying coil is also brought and carried out the same experiment, and they have observed what? A similar deflection have been observed in the galvanometer. What happened? When they bring brought a current carrying conductor, even though deflection were observed in the galvanometer. Deflection were observed. It's confirmed that the relative motion between magnet and the coil, or relative motion between current carrying coil and another coil, it caused deflection in the galvanometer. It means galvanometer only shows deflection whenever there is a passage of current, whenever flow of current through the circuit. Hence it is confirmed that the relative motion between these two can cause the deflection in the galvanometer and hence induction of electricity. Based on this experiment, a new quantity have been introduced that is called magnetic flux. Now we are talking about magnetic flux. We have studied similar kind of things in our electrostatic also, that is known as electric flux, but we are talking about here magnetic flux. What is magnetic flux? Magnetic flux is like flow of something or flow of steam, a stream of water you can assume also, blowing of air or anything, blowing of air through a window, or passage of any river water. We can assume that for net. If we have net for catching the fish, what happens? A flow of water will pass through it. So amount of water that is passing through this net is called flux. In the similar manner, a magnetic flux can be defined as, magnetic flux is what? It could be defined as the number of magnetic field lines, the number of magnetic field lines the number of magnetic field lines passing through a surface normally when placed in a magnetic field. Magnetic field is called what? It is called magnetic flux. It is called magnetic flux. It is called magnetic flux. So the number of magnetic field lines passing through a surface normally when placed in a magnetic field, it is called magnetic flux. It is represented by Greek letter phi. This is called phi. For magnetic field line, we can write it B, and mathematically it is B dot A. It is called B dot A. It's a dot product of magnetic field and area vector. Which kind of quantity this is? This is called scalar quantity. It is a scalar quantity. And its SI unit is, magnetic field is Tesla, and area meter square. So its SI unit is Tesla meter square. Now let us understand about this magnetic flux. Its SI unit is Tesla meter square, and the other unit is phi equals V dot A SI unit is how much? SI unit is Tesla meter square, which is called Weber, which is also called Weber. And 1 Weber equal any other unit? CGS unit is there also. What is the CGS unit? CGS unit is 1 Tesla meter square will become 10 to the power 4 Gauss into centimeter square. Meter square should be converted into centimeter square. So 10 to the power 4 centimeter square. It will becomes 10 to the power 8 Gauss centimeter square. Or it is called 10 to the power 8 Maxwell. 10 to the power 8 Maxwell. 1 Weber equals 10 to the power 8 Maxwell. Maxwell is its CGS unit. Maxwell is a CGS unit. SI unit is Tesla meter square or Weber, and CGS unit is Maxwell. Now, let us understand what is flux. It's a scalar quantity. Okay, let's assume this is a surface. When it is placed in a magnetic field, what happens? The number of field line passing through it. The number of field line passing through it. This number of field line that passes through this surface is called magnetic flux. This is called magnetic flux. If these represented magnetic field lines, and this one is the area vector. Area vector is what? Area vector is a vector which is normal to the surface, that representing the face of the area, face of the surface area. For example, if we are talking about this surface, so this whole surface area is pointing upward. If I am placing like that, now area vector is pointing like this. If I am placing like that, area vector is representing like this manner. So area vector is what? Area vector is a vector perpendicular to the surface. It's a normal vector, right? So number of field line passing through a surface area is called magnetic flux. B dot A. Flux equals B dot A, or we can say B A cos theta. We know from the mathematics, vector mathematics, dot product of two vectors, B A cos theta. So what are the factors on which this magnetic flux depends on? This magnetic flux depends on the three parameters. These are magnetic field, area vector, and angle between the magnetic field and area vector. Now let's understand. Suppose we have a big magnetic field. So what happens? Less number of field line will pass through it. If we have not a strong magnetic field, then less number of magnetic field line will pass through. If we have stronger magnetic field, now then what happens? If we have stronger magnetic field, next what happens? It will happen that more number of field line will now pass through the surface. If we have strong magnetic field, more number of field line will pass through its surface, and hence we can say that flux 2 is greater than flux 1. Flux 2 is greater than flux 1. Why? Because there is a stronger magnetic field. So stronger magnetic field means more number of field line. So more number of field line means more number of flux, more amount of flux. Less number of field line is passing through the surface. More number of field line passing through the surface. So magnetic flux depend on flux. Magnetic flux depends on magnetic field. Number 2, magnetic flux depends on the area. surface area. Magnetic flux depends on surface area. How? If we have smaller area, then less number of field line will pass. If we have smaller area, then what happen? There is a possibility of less number of field line to pass through it. Less number of field line. But if we have bigger area, then what happen? If we have bigger area, then more number of field line could pass. How? We have smaller area, only few magnetic field line were passing. If we have more area, then more number of field line could pass through it. So again, phi 2, this one is phi 1, phi 2 is greater than phi 1. Why? Because area is greater than previous one. Greater the area, greater the magnetic flux. Depends on area. So magnetic flux depends on magnetic field and surface area. Again, what are the other factors? These all depends on the angle between the magnetic field line and the area vector. If we have field lines like, and we have a surface area like this way, we have a surface, this much field lines were passing through it. Area vector is which direction? Area vector is also in this direction. This is the area vector which is normally to the surface. Now, if we place it in such a way that the surface is lying this way, area vector is normally perpendicularly outward. No field line is passing through this surface. What happens? If more number of field line is passing, means what? The surface and field line should be perpendicular to each other, but they should be parallel to the area vector. More field line could pass through one side to another side. But if surface is like this, is it possible now to passing the field line through the surface area? No, not at all. Why? Because angle between area vector and field line is how much? Theta is pi by 2. And here theta is 0 degree. Because V dot A cos theta is 0 degree, means maximum flux could be possible. And if theta is pi by 2, means least or minimum number of flux could be passed. No, not at all. 0. So this depends on three things: magnetic field, area, and the angle between area vector and magnetic field line. So flux depend on cos theta. Hence we can say that flux B A cos theta. In vector form we can write it as B dot A. Right? And we have talked about earlier the magnetic flux is scalar quantity. Its unit is Tesla meter square or Weber, and it is also equal to 10 to the power 8 Maxwell. Now come to the next part. So this is about magnetic flux. What is area vector? How could we find out? Let's understand how to find out the area vector. I'll take one example. If suppose this is a plane X, Y and Z, right? And we have a surface plate here of L, square set of length L. What is the area vector? What is the area? Area is how much? Of course, L square. What is the direction of area? Surface area is direction of how much? It is perpendicularly outward, out of the plane. So it will be K cap. K cap. Okay. If I am placing, take another example. If I am taking on surface in YZ plane, now what happened? My surface is this side. This is also suppose a square. Now area is how much? Area will be same as in previous case, L square. What is the direction? Direction is what? It is I cap. So this is the area vector. Any vector that is acting perpendicular to the surface is called area vector. Okay. Now I would like to talk about the magnetic field's direction. Direction of magnetic field. Two kind of things are there. If magnetic field is inward into the plane, if magnetic field is into the plane or inward into the plane, or we can say inward, it is denoted by cross. It is denoted by cross. Matlab, what is meant? What does it mean? It means if we are talking about the magnetic field B naught, then B naught is K cap minus K cap. It means inward magnetic field, into the magnetic field. If there is an outward magnetic field, then how could we find out the direction? How could we know that which is inward and which one is outward? Outward magnetic field is represented by dot. It is represented by dot. Outward magnetic field. Outward magnetic field is represented by dot. It is outward. So outward means out of the plane. Out of the plane is B naught K cap. If it is minus K cap, it means inward. If it is K cap plus K cap, outward. There is outward magnetic field and inward magnetic field. So we have clear idea about the area vector and the inward and outward magnetic field. So what is happening here? We have so far discussed about the Faraday's experiment and the introduction of new quantity that is called magnetic flux. Magnetic flux means what? Number of field lines that passing through a surface normally is called magnetic field, magnetic flux. And its SI unit is Tesla meter square or Weber, and it is equal to 10 to the power 8 Maxwell. So now we have talked about the direction of magnetic field. Inward magnetic field is represented by cross and outward magnetic field is represented by dot. Inward means B naught minus K cap in x by z plane, and outward means B naught K cap. Right? Now we are talking about Faraday's law of electromagnetism. Based on the experiment, a series of experiments carried out by the Faraday and Henry, he proposed a law. Under this law, we studied that whenever there is a flux change, Faraday's law of electromagnetism. Let's see what is happening here. Faraday's law of electromagnetism. Faraday's law of electromagnetism. Whenever a flux linked with a conductor or a circuit changes, then an EMF induced in that circuit, an EMF induced in the circuit whenever the flux linked with the circuit changes with respect to whom? With respect to time. Whenever a flux linked with the conductor or circuit changes with the respect to time in a circuit, then what happened? An EMF will induce, and this EMF, this induced EMF, this induced EMF lasts as long as magnetic flux continue changing. Flux will change as long as flux will change in the circuit. Up to that, a magnetic flux, and up to that, an EMF will induce in the circuit, and hence a current will induce in the circuit. How long? As long as magnetic flux will change in the circuit. Number two, what Faraday stated that the change in magnetic flux or the induced EMF in the circuit, is directly proportional to the rate of change of flux. The magnitude of EMF induced in the circuit is proportional to rate of change of flux, which is given as E equal to minus d phi by dt. Minus sign indicates that the flux that cause the change, that produce induced EMF, is opposed by the induced EMF itself. Means induced EMF opposes the flux change that produce the induced EMF, which is given by Lenz's law. Okay, now, so this was the Faraday's law. Faraday's law was that, what was the Faraday's law? Whenever a flux linked with a circuit or a conductor changes with time, then this change called what? This change in flux called induced EMF, production of induced EMF, and hence production of induced current. And this induced EMF will last as long as flux continue changing in the circuit. And this induced EMF is equal to d phi by dt. Now we are talking about Lenz's law. Lenz's law. Lenz's law. According to Lenz's law, which was given in 1835, it is given that the induced current or EMF, induced current or EMF flows in circuit in such a way that, or in such a direction that, it opposes the change in flux, which produced it. So according to Lenz, the EMF that has been induced in the circuit, its nature is to oppose the flux change. If flux is increasing, then induced EMF will try to decrease. If flux is decreasing, then induced EMF will try to increase the flux. And this is why This is based on the conservation of energy. This is basically conservation of energy principle. This is called Lenz's law. Hence, we could able to write that EMF equal to minus d phi by dt. Means rate of change of flux is opposed by the induced EMF. Let's take with one example. Let's say if a magnet is brought closer to the coil, north south, hence what happen? When we bring it closer to the coil, what happen? Number of field line passing through the surface will increase. Hence what happen? Flux will increase. Flux will increase. If flux will increase, then what happen? Induced EMF or induced current will try to oppose it. It will try to oppose it in such a way that so that it could repel. So in which direction it could flow? It could flow that in such a manner that it could oppose. If here is north pole, so it will try to make it north as well. So it will flow opposite to the direction, clockwise, anti-clockwise. If the flow is anti-clockwise, it will becomes north pole, anti-clockwise. If it is flowing clockwise, then it becomes south pole. Because flux is increasing, so induced EMF will try to decrease it. Induced EMF will try to oppose the change, because here EMF is going to increase. So induced EMF will try to oppose it to not make them increase. Hence, the flow of induced current will be opposite to the direction. Magnetic flux is increasing inward, so it will try to oppose by creating outward flux. So this is the principle of Lenz's law. We can take another example. And what is the reason behind that? The reason behind that is, if we brought closer and closer, if it will not oppose, then what happen? It will violate the conservation of energy principle. It will violate the conservation of energy principle. So what it will try to bring? It will try to maintain the flux constant. Flux constant. If more and more flux increasing and it supports, then what happens? It will becomes like a premium machine, perpetual motion machine, where no energy is dissipated. Hence, in order to maintain the principle of conservation of energy, it opposes the flow of a change of flux. So direction of induced EMF will be opposite direction. If flux is increasing towards it inward, then it will start creating outward flux, so that flux remain constant. If inward increase means it will produce outward. Let's take few examples. Let's say if magnetic field is increasing, inward, if magnetic field is increasing inward and coil is placed there, then what happen? Flux will increase. If flux increase inward, then what will be the direction of induced current? If it is increasing inward, it will try to do what? It will try to produce outward flux, outward magnetic field. So direction of outward will be how? In which direction? We have learned so far. Outward means anti-clockwise. Outward, anti-clockwise. Right hand rule. Outward, anti-clockwise. Inward, clockwise. So the direction of induced current will be outward. If magnetic field is decreasing, then what happens? If magnetic field is decreasing, then it will oppose the decrease of flux. Hence, what happens? It will try to increase inward by how? By clockwise motion, clockwise movement of current. Hence, it is opposing the change of flux that have produced this inducing effect, that have produced induced current or induced EMF. We can take few more examples. Let's say outward magnetic field we have, and coil is placed in outward magnetic field, and it is if increasing. If magnetic field is increasing, means outward flux have been increasing. Outward flux is increasing. If outward flux is increasing, means what? It will try to oppose it. How? It could produce opposite to the outward flux. It will try to produce inward flux. So it will do what? Clockwise. It will flow in clockwise direction. If outward field is, let's say, decreasing. If outward field is decreasing, then what happens? Outward flux will be decreasing. Flux will decrease. Outward direction. If outward is flux decreasing, it means it will try to create outward flux to oppose its. So outward will be anti-clockwise. I hope you have cleared about the Lenz's law, how it opposes the change of flux in the coil. If once inward edge flux is increasing, it tries to oppose it by creating outward flux. If flux is inward decreasing, it will try to create or increase the inward flux. If outward flux is increasing, it will try to oppose by increasing inward flux. If outward flux is decreasing, then it will produce outward flux to increase the net effect. At any cost, at anyhow, the flux should be constant so that conservation of energy could not be violated. Hence, this is the basic principle of Lenz's law. Now let's take about few problems. We have to determine the direction of induced current in the circuit. Let's talk about, we have inward magnetic field and a rectangular coil is there which is moving with velocity v. What happened? When it enters in the field at the point of entry, what is the direction of induced EMF? What is the direction of induced current? We can take it as, just take the x part of the x length of coil, inward x part, x length. So flux is increasing. Why? Because area is increasing. As it enter inside, more and more area will increase. And flux will increase. So how it could be opposed? It could oppose. Inward flux is increasing. So how it will oppose? By producing outward flux. So outward flux direction will be how much? Direction will be anti-clockwise. If we have outward magnetic flux, if we could have outward magnetic flux and a coil is moving with velocity v, what happened? When it entered, when it entered, what happened? When it entered the field, so outward flux will increase. Outward flux will increase. So what it will do? How could it oppose? It would oppose by producing inward flux. So direction of induced current will be inward, means clockwise. So direction of will be clockwise. This is the case of entry. If we have exiting case, if we do have exit case, how could we do so? If we could have exit case, suppose let's say inward magnetic field is there and a surface is coming out with velocity v. In that case, what happens? In that case, area is decreasing, so flux is decreasing inward. So what it will do? Induced current will flow in such a manner that the inward magnetic flux could increase. So it will flow in clockwise. Clockwise. Because inward is decreasing. If we have outward magnetic flux, if we have outward magnetic flux, and a surface is coming out from the magnetic field, then what happens? Outward flux is decreasing because area is decreasing. So outward flux is decreasing means it will try to increase the flux in outward direction. So the direction of flow will be anti-clockwise. Direction of flow is anti-clockwise. By this way, we could identify the direction of induced EMF in the coil. This was based on the Lenz's law. Now, we are talking about few more problems or concept. Let's talk about motional EMF. Motional EMF, motional electromotive force, motional EMF. So far we have studied about electromagnetic induction is that due to change in the flux of any surface or any conducting coil or conducting circuit, what happened? An EMF have been induced and hence a current is induced in the circuit. So by changing the flux, by changing the magnetic flux, a current can be induced in that conductor. And the same thing is happening here. Let's say we have a magnetic field and a conductor is placed inside a magnetic field. A conductor is placed inside a magnetic field. What happens? If we have a conductor of length L, if we have a conductor of length L, which is moving with velocity v, and it is moving with velocity v in a magnetic field. This magnetic field is inward and this is the length of the conductor and it's moving rightward. Then what happens? We know that when this conductor is moving forward, then what happens? As it is a conductor, they could have a free electrons. They could have free electrons. Now what happened? As conductor moving in a magnetic field, so it experiences force. Along with the conductor, electron is also moving in the direction with velocity v. Here, velocity v, magnetic field v, and the length L, all three are mutually perpendicular. These all three are mutually perpendicular. So what happened? We could have a magnetic force over here. Magnetic force we could give it. It could be calculated as Q V cross V, and direction of this one V cross V will give the polarity of the induced EMF. V cross V. Let's say, understood. This one is magnetic field inward. This is a conductor which is moving rightward. This is a conductor moving rightward. So V cross V, placing the hand in such a way, right hand in such a way that the first vector and crossing it, curling it, the direction of thumb will give the direction of V cross V. This will be V cross V. V, 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 and it will become V cross V. So hence, what happened? The electron, free electron on the conductor, they could also experience the force, and due to F equal to QV cross V is a upward direction for positive charge. For as electrons are the negative particle, so force will be downward. Hence what happened? Electrons start shifting from the top to bottom. Top to bottom. Hence negative charge will accumulate at the bottom and positive charge accumulate at the top. Hence what happened? An electrostatic force will arise here. Q into E. In which direction? As electrons are there, positive charge. So direction will be, for positive charge it is negative, means downward. But is negatively charged particle is there, electrons, so it is opposite to the direction of direction of positive charge, so it will become at equilibrium. So magnetic force is downward direction. Magnetic force is downward direction because of negatively charged particle, and electrostatic force will be upward direction because electrons are what? Negatively charged particle. For positive charge, force acting along the direction of electric field, and for the negative charge it acts opposite to the direction of electric field. So hence F of m equal to F of E until when? Until the equilibrium has been reached. So Fm becomes Fe, till then it will work. Hence we can write Q V cross B equals Q into E. Hence induced electric field equals V cross B. Induced electric field is V cross B. What happened here? A conductor is there, a conductor of length L is there. It is placed in a magnetic field, and magnetic field is inward, perpendicularly inward to the plane, and the conductor is moving forward with velocity v, such that v and L all are mutually perpendicular. As conductor is placed in a magnetic field, it can experience a magnetic force. Same will happen to the free electrons. So magnetic force on the electron will be V cross B, that is upward direction for positive charge. As electrons are negatively charged particle, so force will be downward, magnetic force. Due to this force, electron get shifted from top to bottom. Hence at bottom they could have accumulation of negative charge, leaving behind the positive charge at top. Hence an electric field get induced from top to bottom. So force acting on these Negatively charged electron is opposite to the direction of electric field, F of E. And the magnetic force is acting on the electrons are downward direction, F of M. This thing will continue until the equilibrium achieved. After reaching the equilibrium, it will becomes magnetic force equals electrostatic force. QV cross B equals Q into E. Q will be cancelled out, so E induced equal to V cross B. Now, we know that from electrostatic we know that one concept is there, V equals E dot dl. We know that V equals E cross E dot dl. So what we can write, V equals E induce how much? V cross B into dl. Now it becomes what? V. Instead of V we can write it as E equals V B L. So we have obtained the expression for induced EMF as dLV. This is only possible when all three are mutually perpendicular. It is possible only if all three, that is velocity, magnetic field and length, are mutually perpendicular. If they are mutually perpendicular, then only induced EMF is equal to VLD. If any of the two become parallel, then induced EMF will becomes 0. Induced EMF will becomes 0 if any two of them become parallel. If any two of them becomes parallel, then what happens? Induced EMF will be 0. So, due to motion of conducting wire or conductor, due to motion of conductor in a magnetic field, induce a EMF and it act like a battery. Hence, what it becomes? I am redrawing the picture, drawing the diagram. What happened here? Here, this moving rod or moving conductor will act like a voltage source or battery. If it is moving with velocity v of length L, magnetic field is inward, hence it will becomes equivalent to a battery which is having some resistance of conductor E. And the polarity of this one is given by the direction of V cross B. V cross B, opposite, upward. Hence the direction is plus minus. So this is all about the motional EMF. What happens if velocity is not perpendicular to the length? Then we will do what? Then we will do a simple thing. What we will do? We will take component of velocity. If velocity is not perpendicular, if it is making angle with theta with L, as we can take two component. One of the component will become V cos theta, another one is V sin theta. So E equal to become how much? V B L V sin theta. This depends on the angle theta. Hence we can resolve it into component. So component of velocity parallel to the length of conductor will give 0, no value of induced EMF. But the component of velocity perpendicular to the length of conductor will give us EMF BLV sin theta. So this is all about the introductory topic of electromagnetic induction, and later on we will discuss many more concepts and few more numericals. Thank you.